talk on BNPG games with Altruism. I'm Arnab Maiti, and Parajda is my collaborator in this project. So, the public goods game is a very standard model in game theory. So, typically in this public goods game, players need to decide if they want to contribute to a public project, and if they contribute, then how much. And the outcome of such public projects is typically shared equally by all the players. Now, an important class of public goods game is the binary network public goods game. So here the players only need to decide if they want to participate in the public project or not. So yes or no. In this talk, it's like one or zero. So formally, BNPG games are defined in this way. So we are given an arbitrary graph G as an input, which will be an undirected graph. Each node of this graph will represent a player, and the players need to decide whether they want to participate in the public project or not. Now, we consider this variant of the BNPG game where we add altruism in it. So, formally, along with the undirected original graph, there is a directed altruistic graph which may be directed or undirected, and this graph is usually like a subgraph of this. Like if you consider the undirected version of this should be a sub graph of this graph. So as I was saying, um, a player V, which is a node V in the graph, can make a decision. So we represent its decision by xv. So it can be 0 or 1. So 0 means not participating, and 1 means participating in the project. So if you consider a collection of such decisions by the player, so if there are n players in the graph, so if you consider this set of decisions x1, x2 up to xn, then this is called a strategy profile. And based on the input graph G and the altruistic graph H and the strategy profile X, each player receives a reward UV. So typically, the reward form is kind of broken up in this way. So there is some non-decreasing function GV, uh, which only depends on the sum of the decision of the player V and the number of neighbors of V playing 1. Then there is an additive term uh, uh, where the summation will be dependent on the neighbor of V. All for all neighbors of V, say U, we'll consider the corresponding G function here. So GU XU plus NU, where this NU is the number of neighbors of U playing 1, and this will be like kind of multiplied with some small fraction A, and then there is a cost of participating in the project for the player V. So we'll denote this by CV, the cost of participating in the project. So this is how the reward function looks like. So reward function is also called as utility function. Now, having defined the reward function in this way, or the utility function in this way, so the aim here is to typically decide whether the game has a pure strategy Nash equilibrium or not. So formally, strategy profile x1, x2 up to xn is called a pure strategy Nash equilibrium of the game if no player V can increase their reward by unilaterally deviating from the decision xv. So it means that if other players have fixed their decisions, then the current player V does not gain anything by deviating from their decision. So consider this node, it's playing 1. So if all the other players are playing 101, then this player does not gain anything by moving from 1 to 0, or does not increase the reward by moving from 1 to 0. So the problem statement that we'll be focusing on is that we want to decide the existence of PSNE in a given BNPG game with altruism. So one motivation can be that the social planner can use this to predict the behaviors of a player in the strategic setting. But the main goal is to decide whether we can whether the game has a PSNE or not. So there has been some prior work on this. So it was shown that this problem is NP complete in general. So we'll be first set of results will be like focusing on some particular like special cases and see what we can achieve there. So our main result is to show that if the underlying graph is a tree, then this problem can actually be solved in polynomial time. So in polynomial time, you can decide whether the game has a PSNE or not. So high level idea is as follows. Say for any internal node, we ideally would like to maintain a set of strategy profiles where the particular node V is not deviating from its strategy, assuming that the other players are fixed on their particular actions. So this set can be like recursively computed, like you can begin from child and go to the above node and so on. But the thing is that the number of such strategies can blow up and it can become exponential. So the way we kind of overcome this challenge is to maintain implicit representation of such strategy profiles. uh, the implicit representation only involves the decision of the parent node and the number of children and yeah, number of neighbors of this internal node which are playing one. So this will ensure that the representation is in polynomial size and we end up deciding the existence of PSN in polynomial time. However, it is not so trivial to compute these implicit representations, and it requires a greedy strategy that exploits the definition of PSNE in BNPG games. So we refer the audience to the paper for more details. Next, we look at something called circuit rank. So circuit rank of an undirected graph is the minimum number of edges that must be removed from the graph to make it acyclic. So if the number of if the circuit rank is bounded, then this problem can of deciding the existence of PSNE can be again decided in polynomial time. The key idea is to reduce this problem to the problem of deciding the existence of PSNE in certain trees, and we can do this with the help of minimum spanning trees. Our third like algorithmic result is that if your graph is a complete graph, then you can decide the existence of PSN in polynomial time. And we do this by exploiting some nice structural features of this complete graph, and it's we end up getting a simple algorithm. Next, we move to another version of a problem, which we call as altruistic network modification. So here you are given an input graph G, the altruistic graph H, and a strategy profile X. Now here you are kind of allowed to modify the altruistic graph. So you have to modify in such a way that you add an edge or delete an edge, and there is a cost associated with it. And you have to ensure that the graph H is always a subgraph of input graph G. So if the graph is directed, then the undirected version should be a subgraph of the input graph G. And the aim here is to make modifications in the altruistic graph and make a target profile X a PSNE. Or like if it is not possible, then say no. And this you should do by minimizing the total cost incurred. So typically assume that it is possible to make it a PSNE. So in that case, you have to do it by minimizing the total cost of adding and deleting the edges. So so we have some set of results here. So the first result is that if so just to recollect, like we call this problem as altruistic network modification, in short ANM. So this ANM problem is NP hard even if the input graph is a tree, and we can show this by reducing from the knapsack problem, which is NP hard. Now, if your input graph has bounded degree and the corresponding altruistic graph is undirected, then again this problem is NP hard, and we can show this by reducing appropriately from the 3B2 SAT problem, which is NP hard. However, a surprising thing is that as soon as you make the altruistic graph directed, then in graphs with bounded degree, you can actually find it in polynomial time. So this is like a contrast between directed and undirected. So an high level idea is that for each node we kind of construct a minimum knapsack problem and solve it. And so the number of items will be equal to the degree, and since degree is bounded, so we can essentially kind of do some brute force or something like that, and solve for each node, and we'll end up getting a good set of polynomial results. Now, the last set of result is on mixed strategy Nash equilibrium. So this is a generalization of pure strategy Nash equilibrium where the decision of each player is probabilistic. So instead of like fixing on one action, they decide whether they want to play 1 or 0 with some probability. So it is a well-known result that every finite game has a mixed strategy Nash equilibrium, and it was shown by John Nash. So now one might ask, okay, if the existence is guaranteed, then what is the complexity of finding the Nash equilibrium? And we show that, unfortunately, that the complexity of finding mixed strategy Nash equilibrium in a BNPG game is PPAD hard. So it implies that it is quite unlikely to find a mixed strategy Nash equilibrium in polynomial time. So we again summarize our results. So if we want to decide the existence of BNPG game in a tree or graphs with bounded circuit rank or complete graph, we have polynomial time results. If we want to do that network modification and achieve PSN in some target strategy profile, so those ANM problems, they are hard for tree, both undirected and directed. They are also NP hard for graphs which have undirected altruistic graphs and bounded degree, but we can achieve polynomial time result for directed altruistic graphs and bounded degree. And finally, like if you want to find mixed strategy Nash equilibrium in this BNPG game, then it is PPAD hard. So thank you.